Welcome back to the world of automotive engineering. Our principal purpose for these next two lectures is to follow the transmission of mechanical power from the engine's spinning crankshaft to the vehicle's drive wheels. This function is performed by a system called the drivetrain, consisting of the flywheel, clutch, transmission, driveshaft, differential, and two drive axles. But before we can examine the drivetrain, we first need to look more closely at the mechanical power this system is responsible for transmitting. In our last lecture, we saw that the four-stroke cycle of the internal combustion engine could be modeled as a thermodynamic cycle called the Otto cycle and plotted as a graph of pressure versus volume. Before we continue, I should note that internal combustion is by nature not a true thermodynamic cycle, in the sense that vapor compression refrigeration and the steam power generation cycles are true thermodynamic cycles. In both of these latter cases, there's a working fluid, either refrigerant or steam, that circulates continuously through a closed loop. In the refrigeration cycle, that circulation is from compressor to condenser to expansion valve to evaporator. In the steam power cycle, which is sometimes called the Rankine cycle, circulation is from boiler to turbine to condenser to pump. In both cases, the fluid changes state between liquid and gas, but the fluid itself doesn't change in quantity or chemical composition. In contrast, during the Otto cycle, the working fluid, a mixture of air and fuel, is drawn into the cylinder in discrete batches, and then it's expelled. And its chemical composition actually changes over the course of each cycle through the combustion reaction. For this reason, the Otto cycle can only approximate the behavior of an actual internal combustion engine. In modern automotive engineering practice, the quantitative analyses of internal combustion engines are generally conducted with complex computer simulations. Nonetheless, the Otto cycle still holds great value for qualitative analyses of engine performance, which is precisely how we'll use it today. By the way, this fundamental difference between the internal combustion cycle and true thermodynamic cycles is also important because it's the basis for the name of the internal combustion engine, a system characterized by combustion occurring within the working fluid. The combustion turbine, also called the gas turbine, which we examined in our lectures on electric power generation, is also an internal combustion engine. The coal-fired steam power plant is classified as an external combustion engine because the combustion of coal to supply heat for the boiler occurs entirely external to the working fluid. Now, in the last lecture, we learned that when the Otto cycle is plotted as a graph of pressure versus volume, the area enclosed within the cycle is mathematically equal to the cycle's net mechanical work output. We can use this relationship to determine the engine's most important performance characteristics, torque and power. Recalling that the area within the Otto cycle represents the work of one cylinder, we can determine the total work output of the engine by simply multiplying this area by the number of cylinders, represented here by the variable n. Now, the principle of conservation of energy tells us that the work done by the reciprocating motion of the pistons must be equal to the work done by the rotational motion of the crankshaft, minus any friction losses, of course. And work done by a rotating shaft is equal to its torque times the angle of rotation. Recall that torque is the tendency of a force to cause rotation. When you pedal your bicycle, your foot applies a downward force to the pedal, and that force applies torque to the pedal shaft, in exactly the same way that a reciprocating piston applies torque to a crankshaft. In this equation, the angle of rotation must be 2 full turns of the crankshaft, or 720 degrees, because each 4-stroke cycle rotates the shaft through 2 full turns. But for mathematical consistency, we must express this angle in terms of radians, not degrees. 1 full 360-degree rotation corresponds to 2 pi radians, so the angle of rotation in this case for the cycle is 4 pi. Now, With just a bit of algebra, we can express the engine's torque as a simple function of the area enclosed within the Otto cycle diagram, the number of cylinders times this area divided by 4 pi. Furthermore, the engine's net power output is simply equal to torque times rotational speed, where rotational speed is expressed in radians per second, or with an appropriate unit conversion as the more familiar revolutions per minute, or RPM. Therefore, power too is a function of the area enclosed within the Otto cycle diagram. Let's see if we can use these mathematical relationships and the diagram itself to glean some insights about engine performance. First, on the diagram, this distance represents the total volume of one cylinder, and this distance represents the displacement. That's the volume swept by the piston as it moves from bottom dead center to top dead center. If we multiply the displacement of one cylinder by the number of cylinders in the engine, we get the total displacement of the engine, a number that's quite common in automotive specifications. When you hear an advertisement for a 400 cubic inch engine, that's the total displacement. And as the Otto cycle graph suggests, larger displacement corresponds to larger enclosed area, which means more torque and more power. Larger displacement can be achieved either by using more cylinders of a given size or increasing the size of the cylinders. Increasing the cylinder size has the effect shown here, producing a theoretical increase in both torque and power that's directly proportional to the increase in the volume of the cylinder. Now, another way to increase torque and power is to increase the engine's compression ratio, defined as the ratio of V1 to V2 on our diagram. In this case, the compression ratio is 8:1. To increase it without changing the cylinder size, we would increase the length of the piston stroke such that the air in the cylinder is compressed into a smaller space at top dead center. Here's how the Otto cycle diagram shifts with a change from 8:1 to 10:1. Note that increasing the compression ratio causes the enclosed area to get both wider and taller, resulting in increased torque and power. And unlike the strategy of simply making the cylinders larger, increasing the compression ratio also improves the engine's efficiency, meaning that a larger proportion of the fuel's chemical energy is converted into mechanical energy. That means better gas mileage and lower emissions. But there's a limit to the effectiveness of this strategy. Recall that a diesel engine doesn't need spark plugs because the air is brought to such a high pressure that it combusts spontaneously with the addition of fuel. What happens intentionally in a diesel engine can happen unintentionally in a gasoline engine if the maximum pressure gets too high. When it happens, this phenomenon is called knock because premature combustion causes a characteristic pinging sound. To some extent, knock can be controlled by using high-octane gasoline, which requires a higher temperature for combustion. But ultimately, the compression ratio of a spark ignition engine remains fundamentally limited by this phenomenon. Let's now focus on our mathematical equations for torque and power. Note that power is a function of the engine's rotational speed, while torque is not. Thus, if we graph torque and power versus rotational speed, the ideal theoretical result looks like this. As rotational speed increases, power increases linearly while torque remains constant. It's too bad that real engines don't conform to this theoretical ideal, because if they did, we could just increase power indefinitely by simply increasing engine speed. But in practice, the real-world torque curve for a typical automobile engine looks more like this. As you can see, the curve remains relatively flat through the middle range of engine speeds, from about 2,000 to 4,000 RPM, typically, but it drops off sharply at lower and higher speeds. On the high end, this deviation from the ideal is the inevitable result of mechanical friction, as well as the air resistance associated with the intake and exhaust flows into and out of the cylinders. On the low end, the loss of torque is caused primarily by convective heat loss through the cylinder walls during the compression stroke. These losses cause reduced pressure in the cylinder and, as the Otto cycle diagram tells us, Lower pressure translates into lower torque. Now, power equals torque times rotational speed. So the change in the torque curve from ideal to real world causes a similar change in the power curve. Note that power still increases with rotational speed, but only to a point, after which it drops off very sharply. Beyond this point is the red line. That's the speed beyond which the engine is quite likely to self-destruct. Note also that at the low end, both the torque and power curves stop at around 800 RPM because most internal combustion engines simply won't run at speeds much lower than this. These performance curves for a typical engine vividly illustrate the fundamental challenge associated with the design of the automotive drivetrain. To explain why this is so, let's do some math. How fast do you think your car's wheels are rotating when you're cruising down the highway at 60 miles per hour? Well, we're trying to calculate the rotational speed measured in revolutions per time. We know the vehicle speed in distance per time. So to get from the first number to the second, we just need to multiply the revolutions per time by distance per revolution. Then the revolutions cancel out, and we're left with distance per time. But what is the distance per revolution for a rolling wheel? Well, as you can see here, it's just the wheel's circumference. And now, by dividing both sides of this equation by the circumference, we can solve for the rotational speed as simply speed divided by circumference. The circumference of a wheel is pi times its diameter, and we'll use 25 inches as a typical wheel diameter for a passenger car. The only difficult aspect of this calculation is getting all these unit conversions right to convert miles per hour to inches per minute, and the result is about 800 RPM. So here's the challenge. When your car accelerates from a standstill to highway speed, its wheels accelerate through a range of speeds from 0 to somewhat less than 1,000 RPM. Through this entire range of vehicle performance, the engine should operate in the range from 800 to 6,000 RPM. That's roughly 6 times higher. To translate high engine speed to low wheel speed, some sort of gearing is required. This gearing is the responsibility of the transmission. But before we can examine the automotive transmission, we need to take a quick look at gears. Here we have a pair of gears, rotating discs, each with regularly spaced teeth that allow one gear to turn the other without slipping. And even though the gears are of different sizes, the teeth are all the same size to ensure that they mesh properly as the gears turn. Now note that the small gear is rotating much more rapidly than the large one. How much faster? Well, the diameter of this large gear is 3 times larger than the diameter of the small one. And if you watch carefully, as I rotate the large one through one full rotation, you'll see that the small gear rotates 1, 2, and exactly 3 turns. So the 3-to-1 relationship between speeds is called the gear ratio, and it can be calculated most accurately as the ratio of the numbers of teeth on the 2 gears. Here, the smaller gear has 12 teeth, and the larger one has 36. So our earlier estimate of a 3-to-1 gear ratio was indeed correct. Now clearly, one purpose of the gearing is to change the rotational speed of a shaft. Another is to change torque. How might we convince ourselves of this? Well, note that at the point of contact where the gears mesh, each gear exerts a tangential force on the other. Based on Newton's third law, for every action there's an equal and opposite reaction, we know that these 2 forces must be equal in magnitude. And because the radii of the 2 gears differ by a factor of 3, the torque, that's force times radius, must be 3 times larger in the shaft of the larger gear than in the shaft of the small one. Evidently, gear sets of different sizes provide mechanical advantage, just like the simple machines we examined a few lectures back. And for gears, the mechanical advantage is exactly equal to the gear ratio. Just as simple machines trade force for distance, so these gears trade torque for rotation. The larger gear produces more torque, but it rotates more slowly. The smaller one is faster, but it produces less torque. Now, if we doubled the size of that larger gear, we'd get the 6-to-1 gear ratio we need for our automotive transmission. We could connect the engine crankshaft to the small gear and run the shaft of the large gear back to the drive wheels, and we would have that 6-fold decrease in speed we're looking for, while also gaining a 6-fold increase in torque. But there's a problem. Accelerating an automobile from rest at a reasonable rate requires about 12 times more torque than the engine produces. So a 6-fold increase isn't good enough. And if we increased our gear ratio to 12 to 1, we'd fix the acceleration problem, but we'd create a new one. Note that on this set of performance curves, peak power occurs at an engine speed of approximately 6,000 RPM. With a 12-to-1 gear ratio, our 25-inch drive wheels would be turning at 500 RPM, which corresponds to about 38 miles per hour. Beyond 6,000 RPM, the engine's power drops off sharply. So this car with a 12-to-1 gear ratio would be incapable of attaining highway speeds. On the other hand, if we use the original 6-to-1 gear ratio of my model, we'd incur problems at the opposite end of the performance spectrum. On the highway at 60 miles per hour, our drive wheels would be rotating at 800 RPM, which means that the engine would be running at 6 times 800 or 4,800 RPM. That's pretty high on the power curve. And if we're just cruising at constant speed, we're really not using that much power, or at least we don't need it. Yet we're constrained to use it and to burn more gas than necessary simply to maintain our desired speed. Clearly then, there's no one-size-fits-all gear ratio that will provide adequate performance and fuel economy across a normal range of vehicle speeds. And that's why all automotive transmissions provide multiple gear ratios, which we know as first gear, second gear, third gear, and so on. The purpose of a transmission, then, is to keep the engine within its most efficient range of operation while providing adequate torque across the full range of vehicle speeds. This purpose is accomplished through a gearbox that provides multiple pairings of gears, each with different gear ratios. In first gear, a small driving gear turns a significantly larger driven gear, resulting in substantially increased torque and decreased speed. And successively higher gears provide for increased speed at the expense of torque. Well, that's the concept, but how does a transmission actually work? Let's use a computer model to assemble a typical gearbox for a front-engine, rear-drive, 4-speed standard transmission automobile. And then we'll consider some of the alternatives in the next lecture. This is the input shaft, which connects to the engine. And here's the output shaft, or drive shaft, which sends power back to the drive wheels. Note that the drive shaft has grooves called splines running along its length. We'll see what they're for in just a moment. Now, within the gearbox, power is transmitted from one shaft to the other through a third shaft, called the lay shaft, which engages with the input shaft through a pair of gears that are permanently fixed to their respective shafts. Thus, whenever the input shaft turns, the lay shaft turns. Now, arranged along the lay shaft and drive shaft, we'll see 3 other pairs of gears, corresponding to first, second, and third gear on the shift lever. To keep it simple, we'll start by focusing on just the first gear pair. Note that the driving gear on the lay shaft is significantly smaller than the driven gear on the drive shaft, providing the increased torque and decreased speed we'd expect from first gear. In this pairing, the 2 gears always remain meshed, and the smaller gear is permanently fixed to the lay shaft. However, the larger gear is free to spin on a set of bearings inside its hub. Thus, it's free to rotate independently, and it can't be used to transmit power without being externally locked to the drive shaft. The mechanism by which this gear can be locked to the drive shaft on demand is this toothed collar called the dog clutch, which is engaged with the splines of the drive shaft as shown here. Thanks to these splines, the dog clutch rotates with the drive shaft, but is able to slide freely along its length. When we shift into first gear, the bottom end of the shift lever pulls a linkage that's connected to the dog clutch, sliding it into contact with the gear. Ultimately, these teeth on the gear will engage with a matching set on the clutch, firmly locking the two together. However, before they come into contact, the dog clutch and the gear are typically rotating at different speeds, so the two sets of teeth can't mesh until their speeds are synchronized first. This function is performed by a cone-shaped projection on the gear and a similarly shaped indentation on the dog clutch, which come into contact with each other before the teeth do. This pair of cones is called a synchromesh, and to demonstrate how it works, I'm going to use this wine bottle, this cork, and this hand drill. I'm going to clamp the cork into the chuck of my hand drill, and then, simulating the driving shaft, I'm going to turn my hand drill and gradually insert the cork into the opening of the bottle. Now note that when the surfaces first come into contact, they can rotate with respect to each other. My drill is rotating and the bottle is not. But as I push more firmly inward, the two surfaces come more closely together and the friction between them gradually increases. At some point, that friction becomes so great that the bottle begins rotating along with the cork, and therefore, the speeds of these two shafts are now synchronized with each other. And that is, in essence, how a synchromesh works. Now, on our transmission model, the teeth on the gear and dog clutch can now engage, and the gear is mechanically locked to the shaft, like this. Power is now transmitted from the input shaft through the lay shaft and into the drive shaft through the first gear pair. Next, let's add the pair of gears corresponding to second gear. Note that the dog clutch is symmetrical with a synchromesh on either side. So when we pull the shift lever in the opposite direction, the linkage pushes the dog clutch into the second gear and locks it to the shaft. Power is now transmitted through this set of gears. The first gear pair remains meshed, but because the larger gear is no longer locked to the drive shaft, it rotates independently of the shaft and transmits no power. Now we can add the third gear pair, which requires a separate linkage but operates in exactly the same way. Note that in moving the shifter to the third gear position, we must first move it through the neutral position, which disengages the first dog clutch from both of its associated gears. This mechanism ensures that only one set of gears can ever be engaged at a given time. And so what about fourth gear? Well, I bet you can already see the answer. In the typical 4-speed gearbox, when we pull the shift lever into the fourth gear position, the second dog clutch locks the input shaft directly to the drive shaft. Power is now transmitted directly between these two shafts, effectively bypassing the lay shaft. Now note that for each successive pair of gears, the lay shaft gear is larger and the drive shaft gear is smaller. In my model, these pairs correspond to gear ratios of 3.5 to 1, 2 to 1, and 1.4 to 1. The direct connection between the input shaft and the drive shaft is effectively a 1-to-1 gear ratio for fourth gear. Now this might seem odd because, as we've already seen, at normal highway driving speeds, the drive wheels must be rotating much more slowly than the engine crankshaft. So why is there a 1-to-1 ratio? Well, we'll resolve this apparent inconsistency when we discuss the differential, a geared device that adds its own 4-to-1 gear ratio to the drivetrain. In a 5-speed transmission, there's another pair of gears, typically designed to provide overdrive, meaning that in fifth gear, the drive shaft actually rotates faster than the input shaft. This feature provides significantly enhanced fuel efficiency at highway speeds, but at the cost of significantly reduced torque. That's why when you're driving in fifth gear and you need to accelerate, you'll typically have to downshift to fourth or third gear to make it happen. And what about reverse gear? Well, the ingenious mechanism for reversing the direction of the drive shaft consists of three components. This pair of gears, both permanently fixed to their respective shafts, but not meshed with each other, and a separate linkage with a third gear called an idler at its end. When the shift lever is moved to the reverse position, the linkage engages the idler with the other two gears, like this. When an intermediate gear is inserted between driving and driven gears in this manner, it adds no mechanical advantage. But as you can see, it does change the direction of the driven shaft, which is precisely what we want the reverse gear to do. By the way, you might have noticed that in my computer model, all of the gears except those associated with reverse have their teeth cut at an angle. Called helical gears, they're better suited for transmissions than conventional gears because the angled teeth engage with each other more gradually, reducing both mechanical stress and noise. Well, now that we understand the critical function performed by the transmission, we can look more closely at its connection to the engine's crankshaft. This connection consists of the flywheel and the clutch. As we learned in the last lecture, an internal combustion engine generates power through a succession of discrete impulses, each associated with the explosive combustion of fuel and air in one of the engine's cylinders. With each of these explosions, downward movement of the associated piston applies an impulsive torque to the crankshaft. To smooth out these discrete impulses, a heavy disc called the flywheel is fixed to the crankshaft. And here's how a flywheel works. Note that even though I'm setting the wheel in motion with a series of discrete applications of torque, its motion is quite smooth. That's because the wheel has a high rotational moment of inertia, a property that results from having a lot of heavy material placed out here, away from the axis of rotation. Because of this property, the flywheel resists changes to rotational speed, and as a result, it's pretty hard to get moving. But once it's moving, it doesn't slow down appreciably between these applications of torque. So it runs quite smoothly. And why does this actual flywheel have gear teeth on its outer rim? Well, because these teeth engage with the electric starter motor, which is used to start the engine. Now, affixed to the rear of the flywheel is the clutch assembly, which is used to disconnect the engine from the transmission on demand. The clutch is required for two reasons. First, as we've seen, an internal combustion engine is incapable of running at significantly below its idle speed, typically around 800 RPM. Thus, when the vehicle is standing still, the engine must be disengaged from the drivetrain or it'll stall. Second, because of the tremendous forces that are being transmitted through the gearbox whenever it's in gear, the transmission must be physically disconnected from the engine to change gears. If you've ever driven a standard transmission car and failed to depress the clutch pedal all the way during a shift, you probably created a painful grinding sound that serves as a rather traumatic testimonial to the importance of the clutch. So here's how the clutch works in a standard transmission vehicle. At the heart of this device is a heavy metal disc called the clutch plate, which is rigidly connected to the transmission input shaft and, when the engine is transmitting power to the drivetrain, is pressed firmly against the flywheel by a rigid metal ring called the pressure plate and a disc-shaped spring. In this configuration, the clutch is said to be engaged, and power is transmitted across the interface between the flywheel and the clutch plate by friction. When the driver depresses the clutch pedal, a cable or a hydraulic piston forces this bearing inward. The bearing bends the spring like this, causing the clutch plate to pull away from the flywheel. As a result, the clutch is disengaged and no power transmission can occur. When the driver re-engages the clutch, the pedal needs to be raised very gradually so that the friction between flywheel and clutch plate can gradually bring the speed of the input shaft up to the speed of the engine crankshaft. If you let up on the clutch too quickly, sudden application of torque can cause the engine to stall. Now at this point, we've traced the transmission of engine power from the crankshaft through the clutch, and through the transmission gearbox to the drive shaft. Next lecture, we'll continue rearward to the differential and finish where the rubber meets the road. Welcome to the third in our 4-lecture series on automotive engineering. In the last lecture, we followed the transmission of mechanical power, torque multiplied by rotational speed, from the engine crankshaft through the flywheel and clutch assembly to the transmission gearbox in a front-engine rear-wheel drive automobile. Now we'll continue our journey rearward from the gearbox through the drive shaft to the differential and drive wheels. Now, the automotive drive shaft is normally a hollow tube made of steel or high-strength aluminum. Tubes are highly preferable to solid bars for two reasons. First, for a given amount of material, a tube resists torsion or twisting far more effectively. This aluminum tube and this solid aluminum bar have essentially the same weight, which also means that they use the same amount of material. Yet, I can twist the bar quite easily by hand, like this, while if I apply the same torque to the tube, it produces no discernible twist. Indeed, this tube is over 100 times stronger and stiffer than the bar with respect to torsional loading, even though it uses the same amount of material. The tube is also superior to the bar in bending. Again, I can bend this bar quite easily by hand, like this, but I can't budge the tube at all. This is really important because the drive shaft of a front-engine rear-drive car can be upwards of 5 feet long, sufficiently long for a solid bar to experience problems with both sagging, like this, and vibration. Now, another important characteristic of the drive shaft is its connection to the transmission output shaft at one end and to the differential at the other. This photo of a rear axle nicely illustrates the challenge. Note that the axle shafts, which extend laterally outward from the differential, are effectively part of the vehicle's suspension system. This is a leaf spring suspension, a system we'll discuss in the next lecture. When the vehicle is moving, these leaf springs can flex quite a bit, causing the entire differential to move vertically as well. Consequently, the drive shaft must be capable of changing its angle of orientation without interrupting the transmission of power at a few thousand RPM. Now, this flexibility is provided by universal joints at both ends of the shaft. Let's see how this device works by building one. At the heart of a universal joint is this cross-shaped double axle. And once it's inserted into and becomes part of a universal joint, each of those axles is connected to a hinge located on one of the two shafts that are going to be connected together by the universal joint. Now, I need to assemble the joint. That's going to take a few minutes, so if you'll bear with me. And there we have it, a fully functional universal joint. Now, this arrangement of two hinges oriented perpendicular to each other on top of that double axle assembly in the center allows the universal joint to be rotated in two perpendicular directions, like this and like this. And as a result, when I rotate the shaft, the U-joint transmits power smoothly, not only when the two shafts are aligned, but also when I reorient the shaft in any direction with respect to the second or driven shaft. So now let's talk about the differential, a mechanical device that performs three different functions simultaneously. First, it receives power from a single source, the drive shaft, divides it in half, and sends both halves outward to the perpendicular axle shafts. Second, it increases the gear ratio of the drivetrain by a factor of approximately 4:1. And third, it allows the two drive wheels to rotate at different speeds when the vehicle is negotiating a turn. Now, to illustrate this last function, let's assume you're driving a car and you decide to make a U-turn. Most passenger cars have a turning circle of about 35 feet, meaning that with the steering wheel turned all the way to one lock, the outer wheels follow a circular arc with a diameter of 35 feet. For this U-turn, the distance traveled by your outer wheels is half of the circumference of the corresponding circle, or pi times the diameter divided by 2, which works out to be 55 feet. If your wheels are 25 inches in diameter, then this distance corresponds to 8.4 rotations of the wheel. That's 55 feet divided by the wheel's circumference. Meanwhile, since most cars have a track width of about 5 feet, your inside wheels are following a circular path that's 10 feet smaller in diameter, as shown here. Thus, the distance they travel is a mere 39 feet, or 6 wheel rotations. So, one wheel wants to make 6 rotations, the other 8.5. Clearly, if the two drive wheels were connected together by a solid axle, like these are, then they would skid through the turn, like this. As I move through the turn, I'm going to keep the inside wheel in firm contact with the tabletop, and you'll notice that the only way for that to happen is for the outer wheel to skid significantly as it makes the turn. So how does the differential accommodate this significant difference in rotational speed while continuing to deliver smooth power to both wheels? Well, this model illustrates how the differential accomplishes all three of its functions, though I should add that my rather crude handmade model differs from an actual differential in several key details that we'll discuss shortly. Now, we'll use our U-joint model here to represent the vehicle's drive shaft, providing input to the differential. Out on its end, this small gear is called a pinion gear, and it rotates with the drive shaft. It engages with this much larger gear called a crown gear, so named because its perpendicular teeth resemble the points of a king's crown. Now, note that the crown gear's axis of rotation is perpendicular to the drive shaft. Through this mechanism, the differential achieves its first purpose of dividing input power into two perpendicular axle shafts. So let's give it a try. Now, as I operate the system, note that the small gear on the end of the drive shaft, the pinion, is rotating about 4 times faster than the crown gear. And so this pair of gears, often called the final drive, also achieves the differential's second purpose of increasing the drivetrain's gear ratio. The differential's third purpose is performed by this mechanism out here called a planetary gear set. Its principal components are these two sun gears, each fixed to one of the axle shafts. Note that as I rotate this axle shaft slightly, the sun gear rotates along with it. There are also 2 planet gears out here, and they're configured such that they can revolve around the sun gears. Are you getting the astronomical analogy here? And then finally, this frame, which is called the planet carrier, it holds the planet gears, and it's fixed to the crown gear of the final drive so that it rotates along with the crown gear and can rotate independent of the axle shafts. So now when the vehicle's driving straight ahead, this entire planetary gear set is basically just going along for the ride. The planet gears don't rotate, and the sun gears and axles are spinning at the same rotational speed as the crown gear. But when the vehicle turns, the 2 drive wheels will rotate at different speeds. And as a result, The planet gears rotate to accommodate the different shaft speeds, like this. The planetary gear set causes the average rotational speed of the two sun gears to always equal the rotational speed of the crown gear. Thus, the total power delivered to the two axle shafts doesn't change, but the allocation of power does, with the faster shaft receiving proportionately more power. Now, the key differences between an actual differential and my simple model are all related to the configurations of the gears themselves. In my model, the sun and planet gears are all conventional spur gears. That is, gears with the faces of the teeth oriented perpendicular to the face of the gear. In an actual differential, they're bevel gears like these, which have their teeth set at a 45-degree angle so they can mesh more effectively when they're perpendicular to each other. The actual pinion and crown gears shown here are similar to the helical gears we saw in the transmission gearbox, except that their curved teeth are specially shaped to accommodate placement of the pinion below the level of the crown gear's axis. This allows the drive shaft to be mounted lower than it would be with a standard bevel gear. Now, before the advent of this technology, called the hypoid bevel gear set, front-engine rear-drive cars typically had a hump running right down the center of the passenger compartment to provide clearance for the drive shaft. At the ends of the two axle shafts are the final components of the automotive drivetrain, the drive wheels. But because they're also integral components of the suspension, steering, and braking systems, we'll defer our discussion of wheels and tires until the next lecture. Well, that concludes our journey through the drivetrain of a front-engine, manual transmission, rear-drive automobile. But we really won't have given the drivetrain its due without briefly addressing the two most popular alternative configurations, front-wheel drive and the automatic transmission. Front-wheel drive is easy. Here's the typical layout of the engine and drivetrain in a front-drive manual transmission car. Note that the engine, flywheel, clutch, and gearbox are all essentially identical to the configuration of a rear-drive car, except that this entire unit is turned sideways. The other major difference is that in front-wheel drive, the transmission and differential are integrated into a single unit, properly called a transaxle. And as you can see, the output shaft of the gearbox drives the differential directly with no drive shaft, using conventional helical gears rather than the elaborate hypoid bevel gears of the rear-drive differential. Front-wheel drive has several significant advantages over rear-wheel drive. Elimination of the drive shaft saves weight and thus improves fuel efficiency. The compact, transversely mounted engine transaxle unit allows for a smaller engine compartment and a correspondingly larger passenger compartment. Space efficiency is further improved because the transmission, drive shaft, and differential can't impinge upon either the passenger compartment or the cargo compartment. Placing the engine directly over the drive wheels also improves traction and steering stability, particularly on slippery roads. Front-wheel drive does have its disadvantages, though. For reasons we'll discuss next lecture, anytime a vehicle accelerates, its weight shifts rearward. In a rear-drive car, this shift actually increases the traction of the drive wheels, which is why racing cars and other high-performance vehicles almost always use rear drive. In a front-drive car, this weight shift reduces the drive wheel's traction and can cause the tires to slip, an effect that's exacerbated if you're accelerating up a hill. But perhaps the most important disadvantage of front-wheel drive is that integrating power transmission and steering into a single axle significantly increases mechanical complexity. For example, these axle shafts must be connected to the drive wheel hubs through very sophisticated universal joints called constant velocity joints, or CV joints, which provide for steady transmission of power even as the wheels pivot due to steering and move up and down due to the operation of the suspension system. Still, the predominance of front-wheel drive in all but performance cars and large vehicles today suggests that the advantages of this configuration significantly outweigh the disadvantages in most circumstances. Now, on to the automatic transmission. a system that's fundamentally different from its manual counterpart and quite a bit more complex as well. Now, given this complexity, I can only provide a brief overview of the subject. But if I'm successful in piquing your interest, I hope you'll do some further study using the references I've cited in your course guide. An automatic transmission consists of three major components: a torque converter, a gear unit, and a hydraulic control unit. The torque converter is a fascinating device that serves essentially the same function as the clutch in a manual transmission. It allows the engine to keep running when the vehicle comes to a stop, and it cushions abrupt changes in the relative speeds of the input and output shafts during gear changes. The difference, of course, is that it must perform these functions without human intervention. The torque converter's mode of operation is as surprising as it is ingenious. It couples the engine to the transmission with a moving fluid. Here's how it works. The device is composed of three main components: the impeller, turbine, and stator, as shown here. The impeller is a disc, shaped like a half donut, with a series of radial vanes mounted inside. The impeller is rigidly attached to the torque converter's housing, which itself is bolted to the engine's flywheel. Thus, whenever the engine is running, the impeller rotates at the same speed. The turbine forms the other half of the donut and also incorporates a set of curved vanes. The turbine is contained within the torque converter's housing, but it can rotate independently. Its shaft extends out to the rear, where it serves as the input shaft to the transmission gear unit. The torque converter is filled with automatic transmission fluid. Whenever the engine is running, the centrifugal force caused by the impeller's rotation flings this fluid outward. As the fluid reaches the outer edge of the impeller, it's directed into the turbine and then circulates back inward toward the shaft. Along the way, the fluid flows along the turbine's curved vanes, and its change of direction causes the turbine to spin. As the fluid returns to the center of the turbine, it needs to be fed back into the impeller to continue the cycle. This is the job of the stator, which uses specially designed vanes to redirect the fluid flow into the impeller with minimum power loss. Now, in effect, the impeller and turbine of a torque converter operate like these two fans. One of these fans is connected to power, and as you'll see, the other fan isn't even plugged in. What I'm going to do is turn on one fan, and that mechanically driven fan will represent the impeller driven by the engine's crankshaft. When it spins, it's going to transmit power to the second fan, which represents the turbine. Watch. Note that this transfer of power from the impeller to the turbine is occurring entirely through a fluid coupling. There is absolutely no physical connection between the two devices. And yet power is being transferred quite effectively. Now, in this case, using two fans, the fluid that couples the two devices together is simply air. In an actual torque converter, the more dense transmission fluid does this job far more effectively. And furthermore, the torque converter can serve its purpose as an automatic clutch because the strength of this fluid coupling increases significantly with engine speed. Thus, when the engine is turning at high RPM, the impeller accelerates the fluid to a higher speed, and the fluid drives the turbine more forcefully. When the engine speed is low, the fluid coupling is weak, so relatively little power is transmitted through the converter. And that's why when your engine is idling, you can feel just a bit of forward pull. The car will creep forward if you don't keep your foot on the brake. But the transmission of power through the torque converter is so low that just light pressure on the brake pedal is entirely adequate to prevent the car from moving forward. Well, now we'll follow the transmission of power from the torque converter's turbine shaft into the gear unit. At the heart of this machine is a planetary gear set like this one. Similar to the gear set we saw in the differential, this one uses a central sun gear and two or more planet gears that can revolve around the sun on a rotating planet carrier. But unlike the differential gear set, this one has all the gears rotating in the same plane, and it also includes an additional outer ring-shaped gear called an annular gear. This gear set has a fascinating characteristic that makes it quite useful for transmissions. The mechanism has three main components: the annular gear, sun gear, and planet carrier. And any two of these three can be used for input and output if the third one is locked or constrained. For example, we can use the sun gear as input and the planet carrier as output, and when we lock the annular gear, rotation of the sun gear produces a slower rotation of the carrier. Slower rotation corresponds to more torque, so this arrangement provides mechanical advantage. Or we might use the planet carrier as input and the annular gear as output. When we now lock the sun gear, rotation of the planet carrier produces a faster rotation of the annular gear. Faster rotation corresponds to lower torque. And if we lock the planet carrier, clockwise rotation of the sun gear produces a counterclockwise rotation of the annular gear. So the gear set can be used to reverse the shaft's direction as well. The key feature of the planetary gear set is that all 6 possible configurations can be achieved simply by locking and unlocking components. Changes of configuration can be made instantaneously without the interruption of power input, and the gears remain in mesh continuously. Taking advantage of this very powerful feature, one type of 3-speed automatic transmission provides the 4 required gear ratios, 3 forward and 1 reverse, by linking 2 planetary gear sets together and then using a series of hydraulically operated clutches and brakes to lock and direct input power through different components of the 2 gear sets. This computer model is a highly simplified cutaway representation of just such a transmission. Here are the 2 planetary gear sets, called the forward and reverse gear sets. Note that I've color-coded their components so you can keep track of the interconnections. The 2 yellow sun gears are mounted on a common shaft, and both the forward carrier and the reverse annular gear are rigidly connected to the output shaft. The other key components of the system are 2 clutches and 2 brake bands, all of which are hydraulically actuated. This is called the forward clutch. When it's engaged, it connects the input shaft to the annular gear of the forward planetary gear set. And this is the drive and reverse clutch. When engaged, it connects the input shaft to the common sun gear. These clutches are themselves quite interesting, so we'll return for a closer look shortly. The brake bands are steel straps that, when pulled tight by hydraulic actuators, lock certain components of the planetary gear sets. This forward band is used to lock the sun gear, and the rear one is used to lock the planet carrier of the reverse gear set. And now we're ready to put this gear unit into operation. For all 3 forward gears, the hydraulic control unit engages the forward clutch, which then transmits power from the input shaft to the forward annular gear. And in first gear, this rear brake is also engaged to lock the reverse planet carrier. Now note that the forward planet carrier is rigidly connected to the output shaft. So even though it's not locked, it is constrained to rotate at the same speed as the output shaft. Thus, power is transmitted from the forward annular gear through the forward planet gears into the sun gear. And because both sun gears rotate on a common shaft, power is now transferred from the forward sun gear to the reverse sun gear. The reverse planet carrier is locked by its brake band, so the sun gear drives the reverse annular gear through the associated planet gears. And because the reverse annular gear is rigidly connected to the output shaft, we have a complete path for power transmission from the input shaft through both planetary gear sets to the output shaft. By compounding the mechanical advantage of both planetary gear sets, this transmission achieves an overall gear ratio of about 2.7 to 1 for first gear. And now the worst is over. The remaining 3 speeds are considerably easier to understand because each employs only one of the 2 planetary gear sets. In second gear, the forward clutch remains engaged, So power is again delivered to the forward annular gear. But now the forward brake band is also engaged, locking the common sun gear. With the sun gear locked, the forward annular gear drives the forward planet carrier, which turns the output shaft with a gear ratio of 1.5 to 1. None of the reverse gear set components are locked, so the entire mechanism can spin freely without transmitting any power. In third gear, both clutches are engaged, so power is delivered simultaneously to both the forward annular gear and the common sun gear. Since both of these components are now spinning at the same rotational speed, the planet carrier is constrained to rotate right along with them. This causes the output shaft to rotate at exactly the same speed as the input shaft, achieving the desired 1-to-1 gear ratio in third gear. And finally, in reverse, only the drive and reverse clutch is engaged, delivering power to the sun gear. The rear brake band is also engaged, locking the reverse planet carrier. Thus, the sun gear drives the reverse annular gear in the opposite direction, as you see here, with a gear ratio of 2.4 to 1. Now, I must emphasize that I've been describing one relatively simple type of 3-speed gear unit. Most modern cars incorporate at least one more speed for overdrive, and several manufacturers are now producing transmissions with 6 to 9 forward speeds. These improvements have been achieved primarily by developing clever new pairings of planetary gear sets, with the result that these highly capable transmissions are often physically smaller than the older, simpler 3-speed units. But regardless of size or number of speeds, the basic principles of operation remain essentially unchanged. The required gear ratios are achieved by using clutches and brakes to control which components of the planetary gear sets receive power and which are locked. In this regard, the modern trend has been to replace brake bands with clutches because clutch engagement is generally faster and more precise. Now, with that in mind, we really should pause to take just a moment to examine the hydraulic multiplate clutch that's so integral to all automatic transmissions. The two elements of this device are a hub here, which is normally attached to the driving shaft, that is the shaft that's delivering power, and a drum, which is attached to the driven shaft. Inside of the drum are an alternating series of metal plates and friction discs. This is one of the metal plates. And as you can see, the plate has outward projections spaced around its circumference. These outward projections engage with slots in the inner surface of the drum, like this. The plates alternate with these friction discs. And you'll note that the friction discs have inward projections that engaged with slots in the outer surface of the hub, like this. Now, my simple model has only 2 of each type, 2 friction discs and 2 metal plates. Actual hydraulic clutches actually have many more. So I'll just add the 2 remaining discs. And then I'm going to insert the hub into the drum, as you can see here. And as I do that, I'll insert that last metal disc's projections into the slots in the inner surface of the hub. And now the hydraulic clutch is assembled. Now, as long as the plates contained within the drum are loose, the hub and the drum can rotate freely with respect to each other, and as a result, no power is being transmitted through the clutch, and so the clutch is considered to be disengaged. However, when high-pressure transmission fluid is pumped into the device from this side, it has the effect of compressing the plates and discs together. Friction causes them to lock to each other like this, and as a result, the 2 components now are able to rotate as one, and therefore power is transmitted through the clutch and through the associated shafts. The clutch is now considered to be engaged. It really is an ingenious device. Whether actuated by clutches or bands, the transmission can't operate without its hydraulic control unit. a fluid-powered computer that uses pressurized transmission fluid moving through a series of valves to determine when each shift should occur and then to execute the changes of gears. This diagram shows the control unit for a hypothetical two-speed transmission. Of course, no cars use two-speed transmissions anymore, but through this very simple example, we'll be better able to focus on how the system operates without getting lost in the mind-numbing complexity of the modern systems that offer more options. This simple control unit consists of the following components: the manual control valve, a cylinder containing a spool-shaped piston that's directly connected to the driver's shift lever; the governor, a sensor and valve assembly connected directly to the transmission output shaft; the shift valve, which receives mechanical input directly from the accelerator pedal or the throttle at one end, and hydraulic input from the governor at the opposite end; a clutch, which is used to engage high gear; two brake bands, which are used to engage low gear and reverse. Both of these are actuated by spring-loaded hydraulic pistons called servos; and finally, a system of hydraulic lines which receive high-pressure transmission fluid from a pump and transmit it through the control system in response to three different inputs: the shift lever position, the throttle position, and fluid pressure from the governor. Throughout this system, the presence of high-pressure fluid in any hydraulic line is called line pressure. Now, because the shifter is currently in neutral, the manual control valve is blocking the flow of fluid into the system. When you shift into reverse, the piston slides to the right, and the valve now supplies line pressure directly to the reversed band servo, which shifts the transmission into reverse. Similarly, in low gear, line pressure is rerouted to the low band servo, and the transmission now shifts into low gear. When you move the shifter to the drive position, line pressure is now supplied to both the low band servo and the governor. Now recall that the governor is connected directly to the transmission output shaft. So the governor's rotational speed is a direct measurement of the vehicle's road speed. When the governor's shaft is spinning slowly, these two spring-loaded arms remain close to the shaft, and this valve then remains closed. But as the road speed increases, the shaft rotates more rapidly and centrifugal force pulls the arms outward like this, gradually opening the valve and allowing progressively more high-pressure fluid to flow through the governor and into the shift valve. The position of the shift valve's piston is now determined by the relative strength of these two inputs, throttle position and road speed. If your road speed is high, but you aren't putting much pressure on the accelerator, it's time for an upshift. Because of the high road speed, full line pressure from the governor overcomes the resisting force of the valve's internal spring, and the piston slides to the left. Then this valve opens and line pressure is supplied to both the clutch, which engages high gear, and the lower half of the low band servo. And because the bottom of this servo's piston has a larger surface area than the top, the upward force due to fluid pressure exceeds the downward force. The piston moves upward and low gear is disengaged. The transmission has now shifted into high gear. On the other hand, if your road speed is low, but you're applying a lot of pressure on the accelerator, it probably means you're either climbing a hill or accelerating rapidly, so a downshift is needed. The large input force from the accelerator moves the piston to the right, and line pressure to the high gear circuit is cut off. The piston in the low gear servo is now forced downward, and the transmission shifts into low gear. Wow, this is a beautiful system. And while this example is simple in concept, I must emphasize that an actual hydraulic control unit is far more complex. In part because of this complexity, some state-of-the-art transmissions have now switched to electronic control systems that eliminate much, though certainly not all, of the hydraulic hardware. Our exploration of the automotive drivetrain is now complete. In the next lecture, we'll complete this introduction to automotive engineering with an overview of the three systems that help you keep the car on the road: suspension, steering, and braking.